This is called charging by induction. Now we're going to start out the same way we did the first time. We're going to start out with a conductor, a charged conductor, and an uncharged conductor. Again, we'll assume same shape, same size. Now what we're going to do is we're going to bring this second conductor over toward the first one, but we're only going to bring it near to the first one. We're not going to actually allow them to touch each other. So I'm going to bring this one over here. Now what happens? Well, let's remember, this is a conductor, so it's got charges inside. It's made up of atoms which have positive and negative charges. The charges in that conductor are still going to feel the force from the negative charges over here. So the negative charges in here are going to be repelled by the negative charges over here. They're going to be pushed over to this side, which is going to leave the side that's closer to this one with a positive charge. So while the entire conductor still has zero net charge, those charges have separated from each other. Now let's imagine we take a wire and connect it to this conductor and actually sink that wire into the ground. Physically just stick it into the ground. This is what we call grounding the conductor, and physically we really mean just stick it into the ground. When you've got, say, a three-prong plug and we say one of those wires is a grounding wire, if you follow that wire from that plug, it will actually go outside to a long piece of metal that's actually stuck down into the ground. It is physically grounded. Now, the reason that we do that is because what's going to happen now to the charge on this conductor? Remember, those charges are trying to get toward the negative charge if it's the positive charge, and the negative charges are trying to get as far away as possible. So these negative charges will actually run down this wire and go down into the ground that's connected to the rest of the earth. The earth is so big that these charges can actually go down there and spread out and get far enough away that they have very little effect on each other. So by grounding something, you're giving it a place where all of these extra charges can just go and get away from each other and spread out as far as possible. The positive charges, however, will stay here because they're being attracted by the negative charges. We then, let's imagine, disconnect our grounding wire, leaving our conductor with that positive charge still there. And now we move this conductor away, and it comes over here, and it now still has those positive charges on it, which separate as far as possible, and we end up with this situation. We say that we have now charged this conductor by induction. What have we ended up doing? Well, we have not changed the charge on this one at all. It still has exactly the same charge we started with. This conductor now has an opposite sign of charge as the original conductor. Remember, when we charged by conduction, this conductor ended up with the same sign of charge. By induction, this ends up with the opposite sign. So if that was negative to begin with, this one is now positive. So we've got these two different methods of charging things: charging by conduction, charging by induction. Now, that's pretty much all I'm going to say about this. I just wanted you to see that because there is a possibility that you might need to know that for one of those standardized tests, as I mentioned before. Okay, now let's go back to this force between different charges, and we're going to look at it in a more quantitative fashion. We know that the positive charges are attracted to negative, repelled by positive. Negative charges are repelled by negative, attracted by positive. But how much so? What's the magnitude of this force? Well, this was actually worked out by an individual by the name of Charles Coulomb, after which the unit was named, who lived from 1736 to 1806. And let's imagine we have two charges. So here are two charges. We're going to assume that they are point-like charges. So we're going to assume they're basically small in size compared to the distance between them. Now, I'm not sure why this is true, but it is. Charges are typically indicated with the letter Q. I don't know why Q, but historically, Fred, who is behind the camera there, Fred, any idea why?
I have no idea.
Fred says he doesn't know. So, Q, anyway, sometimes lowercase q, sometimes capital Q. So, let's call this charge Q1 and this charge Q2. And we'll assume that both of them are charged. So, if one of them were neutral, we'll assume there was no force, but we'll assume that there are charges. And let's assume that the distance between them is some distance r. Now, be careful. Do not think r means radius. R is just the distance between them. It's not the radius of anything. It's just the distance r. What Coulomb discovered was that the force between them, now this could be an attractive or a repulsive force. Attractive if they're unlike charges, repulsive if they're like charges. The force was proportional to, and I'm going to use this symbol, sometimes it's kind of drawn like that. I'll just typically draw it as a circle and a half circle, means proportional to. That the force, and it's the same force on both in magnitude. So the force that Q1 exerts on Q2 is the same magnitude that Q2 exerts on Q1. If we remember that from Newton's second law. Newton's third law. What F is proportional to is the magnitude of Q1. So that the larger Q1, the greater the force that's exerted on Q2, but likewise the greater the force that's exerted on Q1. It is also proportional to the magnitude of the charge Q2. The bigger Q2, the greater the force on Q1, and likewise the bigger Q2, the bigger the force on Q2. It also depends on the distance between them. In this case, if we increase the distance, we decrease the amount of force. So it decreases as we increase the distance, but not linearly inversely. It is inversely proportional to the square of the distance. So if we double the distance, we have 1/4 the amount of force. If we triple the distance, 1/9 the amount of force. We can write this out as a single equation in that F is equal to the magnitude of Q1 times the magnitude of Q2 divided by r squared. And then we have a constant of proportionality, which we will call K. K is referred to as the Coulomb constant, or Coulomb's constant. And K has a value of 8.99 times 10 to the 9th, and then in SI units, to get newtons, when Q is in coulombs and R is in meters, K will be 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. So there we go. That's the value for Coulomb's constant. Okay. Let me just mention that sometimes there's another form of a constant that we'll use, and that is, it turns out that a very common combination of K is 1 over 4 pi K, and that's just another constant. This is referred to as epsilon naught, or the permittivity of free space, and we'll see that more later on. Typically for now we'll just use K, but keep in mind this epsilon naught, we'll see it later. It has a value of 8.85 times 10 to the minus 12, and then the units are exactly the inverse of the units of K. Coulomb squared per Newton meter squared. Okay, there we go. Now, let's stick some numbers in. Let's look at some problems. Let's imagine that we've got two charges, 1 Coulomb and 1 Coulomb. They're both positive. And let's assume that they are separated by 1 meter. Okay, first of all, what's the direction of the forces? Well, we know that positive charges repel each other. So the direction of the force on this Coulomb will be exactly away from that one. And the direction of the force on that one will be exactly away from this one. So the force will be that way. So notice they are in opposite directions, as we would expect from Newton's third law. What's the magnitude of the force? Well, let's remember F is equal to K, magnitude Q1, magnitude Q2, over R squared. So K is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, times magnitude of Q1, call this one 1 Coulomb, times magnitude of Q2, we'll call that one Q2, 1 Coulomb, over R, which is 1 meter squared. And what do we get? Well, we get 8.99 times 10 to the 9th. Notice Coulomb squared, meter squared, newtons. 8.99 times 10 to the 9th newtons. In other words, about 9 billion newtons. Well, that is a huge, huge force, 9 billion newtons if you think about it. Well, what does that tell us? Well, that tells us that typically the charges that we will be dealing with in ordinary everyday life are not going to be on the order of a size of 1 Coulomb. We're going to be talking about much, much smaller charges because we're not going to be dealing with forces that big. We're typically going to be dealing with things like millicoulombs or microcoulombs or nanocoulombs. So very much, much smaller charges. All right, let's try another one. Start out with a coordinate system. Let's put a charge at the point 3 meters, 2 meters. So 3 meters, 2 meters. So right there, we'll call this Q1. And we'll put a charge of 3.27 microcoulombs. And then we'll put another charge at the point 6, 9. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So up here at the point 6 meters, 9 meters, we'll put the charge Q2, and Q2 will be 5.36 microcoulombs. There we go. And that's the 0.32. And the question is, what is the force on Q2? So what is F2? And that's a vector, so we're looking for the vector F2. Well, first of all, let's sketch in. What is F2 going to look like? What's its direction? Well, we've got two positive charges here, so the force on Q2 will be repelled. It's going to be pushed away from Q1. So we expect the force to be away from Q1, so it's going to look like that. Okay, keep in mind, when you draw the vector, start the vector at Q2 and go away from Q2. So imagine you're pointing with your finger. So start your vector from your body and point away, like your arm would point away from you, whatever the direction is. So here we're going to start the vector at Q2 and then point away. It would go away this way if it were away from Q1. We draw it this way if it were toward Q1. But always start the vector on the charge. There we go. So there's the direction. Let's figure out what's the magnitude. Well, remember the magnitude, F2 will be K, Q1 magnitude, magnitude Q2 over R squared. So what's K? 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, times the magnitude of Q1, which is 3.27. Now let's put it into SI units. So microcoulombs, that's times 10 to the minus 6 coulombs, times magnitude of Q2, 5.36. Again, microcoulombs, so times 10 to the minus 6 coulombs, over R. R is the distance between the charges. Now to figure out that, we're going to have to use Pythagoras. So we'll make a right triangle here. Now let's notice, we're going from x equals 3 meters to 6 meters. So this side will be 3 meters long. And we're going from y equals 2 to y equals 9. So that's going to be 7 meters long. So what's r? R will be the square root of 3 meters squared plus 7 meters squared root, or that is 7.62 meters. There we go. So this is going to be divided by 7.62 meters squared. Divide that out, and what do we get? We get a magnitude of the force of 2.71 times 10 to the minus 3 newtons. There we go. So there's the magnitude. Now what's the direction? Well, to find the direction, we need to know the angle between the vector and some axis. So we might say if we could find that angle, we would know the direction. Well, notice that that angle, because this is along a line, is the same as that angle. So how do we find theta? Well, we can use this triangle right here. We know tan theta is equal to opposite over adjacent. In other words, 7 meters over 3 meters. Divide that out, take the inverse tan, and we find theta is equal to 66.7 degrees. So what is F2? F2, we can write all together. F2 is 2.71 times 10 to the minus 3 newtons at an angle of 66.7 degrees above the x-axis. There we go. And there is F2. Now, what if we wanted to know F1? What is the force on Q1? Well, notice the force on Q1 will be away from Q2, so that would be in exactly that direction. Well, what's that? Well, we could go through this whole thing and figure that out, or we can realize the magnitude of F1 must be exactly the same as the magnitude of F2. And what's the direction? Well, if it is directly opposite that, we know it's got to be that same angle theta, but below the negative x-axis. So F1, we could say, F1 is 2.71 times 10 to the minus 3 newtons at an angle of 66.7 degrees below the negative x-axis. So we can say what F1 is very easily once we know what F2 is. Okay, now what if we had more charges? What if we had, let's say, Q3? How could we determine the net force acting on Q2? Let's say we had Q1 and Q3 creating a force on Q2, and we wanted to find out what the total force on Q2 was. Well, we find the force due to Q1, which is what we did here. Then we find the force due to Q3. Maybe Q3 is a negative charge, and we have some force that looks like that. So we figure out the magnitude and the direction of this force. What's the total force? Well, the total force will be this vector plus this vector. How do we add vectors? Well, we know how to add vectors. We break them down into components. This would have a positive x component, a positive y component. This one, if it's in that direction, would have a negative x and a negative y component. You combine the x components, combine the y components, and then put them back together just like we've always done with anytime we had to add vectors, recombine them to find the magnitude and direction. Now, hopefully you remember how to do that. If you don't, there are some examples on the homework. You can work on those, and hopefully that'll refresh your memory. Okay, well that is all for this lecture. Next time, we're going to start looking at the electric force in a little more detail. We're going to look at it in a little different way. How can we define where this force is coming from? And well, I'll just leave it at that. How can we get an idea of where this force is really coming from? Okay, see you next time.